Okay, hello Analysis 1A. We're going to go over the homework that was due on Thursday and Friday. We did some of it in class, and this is Thursday afternoon, so in periods 3 and 4, and I assume also this will happen in period 6. We went over 94 and 95 from section 3.1, so this is the section that's still just teaching you kind of like what differentiation is. Let's go over the rest of these problems. Not all of them are super hard or maybe worth going over, but I don't know, this subject that we're going to do right this second is a little bit hard, and this is kind of just a repetition of the problems that we went over in class, last class. But now this was like extra practice, so sort of, you know, no excuse not to get it or something like that. This limit as x approaches 9 of, okay, so here what's happening is you are given two limits, and so once again the goal is to not necessarily do the limits, which could be easily just computed using knowledge of limits, even if you didn't know anything about derivatives. But the task actually is to understand the definition of the derivative so well that you recognize these limits as derivatives, and then tell what the function is which is being differentiated and where. Maybe we'll do this one first because somehow it's easier or something. So we're taking the limit as x approaches 9. And there's some function, so I won't draw the function accurately because I don't know what the function is yet. So I'll just draw a generic function, and then something is happening at 9. What's happening? Well, I have a point x, which is a little bit more or a little bit less than 9. And yeah, what is this? Well, it's 9 comma f of 9, and then this is x comma f of x. In other words, I suspect that this limit is a derivative. And so let's try to figure out what's the derivative of. I draw the secant line, I draw the triangle, so this is still working on, you know, just recognizing or understanding what a derivative is. So this is f of x minus f of 9. In other words, I'm kind of just going through the logic all over again one more time, that the derivative of some function at 9 is the limit as x gets really close to 9, so the derivative is the slope of the tangent line to the curve. What's the tangent line to the curve? It's what you get when you move the 2 points of the blue secant line infinitely close together, and the slope of that blue secant line is f of x minus f of 9 over x minus 9. Okay, and now looking sort of up at my original limit, it seems that this will all make sense as long as f of x is the function 2 root x. And what is f of 9? Well, it's indeed 6. And so this problem is kind of just done. And what do I mean by done? Well, I guess what I mean is that this is the derivative at 9. So the answer is that this is just f prime of 9, where 9 is where f is the function 2 root x. By the way, you know, follow up. We can just do this limit, so let's do it. It's the limit as x approaches 9 of, I can factor out a 2 here, so that gives me 2 root x minus 3. And the smooth thing to do is to factor x minus 9 as root x minus 3 root x plus 3, cha-cha. And then, you know, this cancels. So we get the limit as x approaches 9 of 2 over root x plus 3. And then I guess that's just like 2 over 6. So that is 1/3. Okay, so even if I didn't know anything about differentiation, I could tell you that this limit was just 1/3 by simply doing it. But the thing is, I do know something about differentiation. Now, I know that this function, 2 root x, can perhaps best be written as 2x to the 1/2. And if you're willing to accept that the power rule also works for power functions with fractional exponents, it was a pretty convincing argument in class that this was the case, then we can just differentiate this function according to the rule, as in not using limits at all directly. What do we get? We get, bring down the 1/2, so that becomes just x to the negative 1/2. So this is 1 over root x is the derivative of this function in general. And, well, what do you know? If you plug 9 into this formula, then you do get 1/3. So it's kind of like, oh, making sense. Okay, back up here. Maybe we didn't need to go over this, I'm thinking now. But, okay, too late. What now? Well, now this is the other definition of the derivative in which delta x, the sort of gap between the point of interest and the other point is becoming infinitely small. What is that point of interest? Answer, it's like -2, it seems. So here's -2. Okay, this is kind of comically not accurate graph, but I don't care. And if this is -2, then I choose to call the point that is slightly more or less than -2, -2 plus delta x. Okay, this is just meant to remind me about the logic of what's going on. This is my point. It's -2 comma f of -2. And this point here is -2 plus delta x, comma f of -2 plus delta x. Boom. And once again, I can draw the secant line. Once again, I can draw this triangle, which tells me that the change in x is delta x, and the change in y is f of -2 plus delta x minus f of -2. And so I can write an expression for the slope of that secant line. It's just f of -2 plus delta x minus f of -2 all over delta x. And if I take the limit as delta x goes to 0 of this whole thing, then that's going to give me the slope of the tangent line, which is what happens when the 2 points move infinitely close together. Excuse me. Alright, well, I think it's just kind of obvious that the function under discussion from comparing, I suppose what I'm doing is I'm comparing, you know, this to this, and from this it seems obvious that the function is the cubing function. So I think that this function is just x cubed, and what is f of -2? Well, it's -8. And notice this is minus f of -2, so perhaps it's a little bit cleaner to rewrite the original problem slightly like that. Now it makes just total sense. Okay, so what is this? This is just f prime of -2. And, you know, once again, we're free to just do this limit. So if you give me -2 plus delta x cubed plus 8 over delta x, and alright, we've come this far, so okay, let's just do it. Maybe this is not essential, but I can just do this limit even if I didn't know anything about derivatives. How? Expanding this out, that would give me -8 plus 3 times this squared times this, so that's going to be 3 times 4, so that's 12 delta x, and then plus 3 times one of those times 2 of those, so that's -6 delta x quantity squared. I'm just doing the binomial theorem, or rather I'm just applying the formula for cubing a binomial, same thing I guess. And then this is plus delta x quantity cubed, and then plus 8, and then the whole thing is over delta x. But okay, the 8s and the -8 cancel, and everything has a delta x in it, so I end up with the limit as delta x goes to 0 of 12 minus 6 delta x plus delta x quantity squared, and as delta x goes to 0, this is just 12. Hopefully I did that right. I can check it because now I have the power rule. And what is the derivative of x cubed? It's 3x squared. And so what is the derivative at -2? Plugging that in, it's indeed 12. And so this whole thing is just working out. Okay, good. So that was 50. Okay, 54 and 56 are kind of thinking, drawing problems. Let's just do those now. Instead of restarting the video, sorry. Okay, 54 says, assume that, oh no, here we go. F of 0 is 4, they tell me. The derivative at 0 is 0. The derivative is negative for negative x. And the derivative is positive for positive x. And okay, this is supposed to just strengthen your understanding of kind of what a derivative is by forcing you to draw a sketch of a function that meets these requirements. Well, okay, hopefully this wasn't so hard. What does it mean for, okay, let's just start, right? If f of 0 is 4, then I have a dot here. If the if the derivative of f at 0 is 0, then it means that the slope of the tangent line to the curve is 0 at x equals 0. So I can draw in a kind of like little tangent line here, and I can know that, yeah, the tangent line is going to have slope 0, in other words, be horizontal. And now, the derivative is supposed to be negative for negative x and positive for positive x. Well, what does that mean? What does that tell me sort of about the function? If the derivative is negative, well, the slopes of the tangent lines are negative. So now all I need to do is kind of just draw, that seems to do just fine, an example of a function where all of the tangent lines have negative slope for negative x values, but then on the right hand side the slopes are all have positive, the tangent lines all have positive slope, so there it is. Of course many different kinds of functions are possible, but a nice function like x squared plus 4 would do just fine here. Okay, 56 I think is a little bit more involved, but it's also just kind of picture writing. There's no proof or anything. So here we go. We have some function f, and here's what we're told. That the derivative of f at c is 3. And then there are two sort of follow-up questions. Answer what the derivative at negative c is if f is odd and if f is even. Okay, so part A, f is an odd function, so f is odd, and part B, f is even. Okay, well, what does it mean to be an even function? Maybe we'll do that one first. If f is even, by definition, that means that f of negative x is just f of x. In other words, the function is doing the same thing on the left-hand side. Well, okay, I don't think I need to reteach this topic, but if a function is even, then at any particular x, if you look at the opposite of that number, the y value is the same. So the function is symmetric across the y-axis. The y values are the same for a number and its opposite. All right, what does that tell me about the derivative at c being 3? Okay, well, I guess it doesn't even really matter if c itself is positive or negative. I don't think they say. No, but I think I'm free to, so it must not matter. So, so here's c. And okay, the output also sort of doesn't matter. So I'll just call that, you know, f of c, that y value. But what can I say about this function? Well, I can say that the derivative is 3 there. If the derivative is 3, then the slope of the tangent line is 3. And so I just really have to just draw in a tangent line there with slope 3. That's roughly slope 3. And okay, if that's true, then I have no idea what this function is doing anywhere else. But near C, you know, it has a tangent line with slope 3. Okay, so what's the significance of this for f of negative c? That's the question, right? Well, okay, I now just use my knowledge of even functions to say that whatever this function's doing, well, by definition, in fact, it must be also have the same y value f of c over here at negative c. But okay, if the function is just symmetric with respect to the y-axis, then if this function if the function looks like this over here near x equals c, then near x equals negative c, it's going to look like this. Okay, so this is basically just kind of a common sense drawing exercise, but I think we all agree that this line has slope negative 3. And all right, if you're looking for a deeper explanation here, deeper explanations are possible, but I think they sort of miss the point a little bit. But if you really want more, you could consider a tiny point like, you know, c plus x, say. And that's going to be just a little bit more, right? And if that's the case, then because this line has slope 3, you know, it's going to be up there. Okay, well, since this function is even, then this extra little point over here that's really close to negative c. Well, now it's like negative c, you know, minus x is the corresponding point. And so on this graph, you know, it's gonna look, it's gonna be over here. This is kind of a waste of time, but it means that yeah, it's not, you're not just fooling yourself that the slope is negative 3. It really is, because you could look at sort of the change in y between a point just to the left of negative c and a point just to the right of negative c, and because this function is even, that's kind of the answer. So okay, conclusion, part B. This is not a proof. This is a just intuition or something, or determination that if f is even, and I know that f prime of c is 3, then f prime of negative c is negative 3. Okay, good. What does it mean if f is odd? The definition of what it means to be odd is that f of negative x is negative f of x. So now, if I go to draw, well, I shouldn't draw 3, I should just draw kind of a generic point c, and if this is f of c up here, boom, then according to the definition of odd, when I go to evaluate f of negative c, it's going to be the opposite of f of c. Okay, and this is what we know about odd functions, that they're kind of like, look like this. They're symmetric with respect to the origin, so 180-degree symmetry with respect to the origin. Okay, well, what was the original problem again? That the derivative of f at c is 3, which means that the slope of the tangent line here will be 3. And what does the function look like? Well, I don't really know, but locally it's gonna have slope 3. All right. Well, if this has like 180-degree symmetry, then basically whatever's happening here, like the same thing is gonna happen here, basically. And so this is even more casual than the previous example, but this line is also gonna have slope 3. Reason? Just like picture, man. And maybe I'll leave it at that, because I think that's really all that was intended. You know what odd functions look like, and once again you could choose kind of like another point, I suppose, but I don't know. I don't want to. So what's the answer to this part A? If the f is odd, then f prime of c will also be 3. Okay, good. That was a visual exercise. Let's do 103. So it's kind of a hard problem. And, you know, arguably, maybe this was a little bit too hard or something. It's kind of a theoretical question. And yet, it does exhibit a certain kind of function that we maybe care about. So, what was this problem? It introduced two functions. This is like, again, the emergence of this sine 1 over x thing, which serves as a useful example and counterexample in calculus. So here we have this function x sine 1 over x, but it's not actually exactly the function that we care about. What is this x sine 1 over x function again? Well, if you just ask me to graph, you know, x sine 1 over x, well, I need to go through the whole logic again. So this is really hard, but we've done this already 5 times. That, you know, sine 1 over x is between -1 and 1. So x sine 1 over x is between negative x and x, at least for positive x. And so the graph of this thing is going to, and this function is going to be even because 1 over x is odd, and sine is odd, the composition of two odd functions is odd, x is also odd, the product of two odd functions is even, or you can just prove it from scratch. And we even saw, you know, last week that the end behavior is 1. And so, for the, like, you know, 5th time or something, I shall graph this function. It looks like this, and then it kind of does, and then it's even, so, alright. So this function is kind of crazy. I wish I'd drawn that a little bigger, but too late. And yet, of course, this function is undefined at 0. But, in fact, what is the limit as x goes to 0 of x sine 1 over x? Well, here we have a now classic opportunity to use the squeeze theorem. And the answer is that this limit is 0. That's because our function, and maybe I'll put a little a box around it right here and not actually write everything all out, but our function x sine 1 over x is bounded by the negative x function and the x function, and of course they're both going to 0. At 0. Okay, so your eyes do not deceive you. Of course, this function near 0 is near 0. It has a limit of 0. But the function is also undefined at 0. Okay, and therefore, the way we should be sort of thinking about this function, this x sine 1 over x function, is kind of like having a hole here, and what's happening is some kind of like infinite oscillation, and this sort of infinitely oscillating. And now, that's kind of annoying, right? Because this function is not continuous at x equals 0, because it's undefined at 0. But its limit is 0, and so this is why we call it a removable discontinuity. The discontinuity is removable because it's possible to remove the discontinuity simply by adding in one extra point. So if I just force this function to have value 0 at x equals 0, well then it will be continuous. Alright, so that is what's kind of happening here. That's what, oops, that should have said not 0. That's kind of what's happening here in this f function. This f function is a function which took a known function, x sine 1 over x, and like patched it up with one extra point, 0, at 0 comes 0, and now, like, it's continuous. And so, that is exactly what the first part of this problem asks. The first part of this problem says, show that f is continuous at x equals 0. So show f is continuous at x equals 0. Well, you know what exactly it means for a function to be continuous. What is the definition of continuity? Well, the limit as x goes to 0 of the function has to be f of 0. So that's the definition of continuity. Whatever a function is promising, it is going to do, it in fact does. So just using the technical definition of continuity at a point, we say that the function is continuous at 0 if the limit as x approaches 0 is actually the value of the function at 0. But we explicitly, or we forced the function to have value 0 at x equals 0 by defining it that way. And we've already seen by the argument I just made below that via the squeeze theorem, this limit of this function is 0. And therefore, these are equal. The function does have a limit, it's 0. It's defined to be 0 at 0. Those two are equal, so the function is continuous. Okay, and now the book says, show that it's not differentiable at x equals 0. Okay, well, what is the derivative at x equals at 0? It is, by definition, the limit as x goes to 0 of f of x minus f of 0 over x minus 0. That's just the definition of the derivative at a point. Okay, so that becomes the limit as x goes to 0 of, what is f of x? Well, it's, for x not equal to 0, it's just x sine 1 over x. And then f of 0 is just 0, and the bottom becomes just x. So if you just kind of like don't think about it too much maybe or something, and just simply just apply the definition of the derivative, you get a certain limit. You sub in all the various things. These are both 0, so they disappear. This divides, and we get the limit as x goes to 0 of sine 1 over x. And what is that? Well, that requires a bit of background knowledge, which you have, which is this sine 1 over x function, which, okay, well now we've sort of seen this sine 1 over x function now sort of many times. What does it look like? It's bounded between -1 and 1. It is odd. Its end behavior is 0, and it kind of comes up and down, and then near 0 it just goes like insane. So this is a function which is infinitely oscillating up and down between -1 and 1 near 0, and so this limit does not exist. And since this limit does not exist, and since the derivative of f at 0 is a limit, then we say that this limit does not exist, and the conclusion is that f is not differentiable at x equals 0. Okay, so here we have a function which is continuous at 0, but not differentiable there. And, okay, on some sort of deep level, why is this function not differentiable? Well, okay, what's happening with this function is this sine 1 over x function has this kind of infinite oscillation, right? Infinite oscillation, up, down, up, down, up, down, up, down, near 0. Here, this function is just like that, except it's being kind of like controlled within this like y equals x, y equals negative x kind of straitjacket. And so it's being squeezed by these two pieces of bread, right? These two policemen have this, function as their prisoner. And so, since they're both going to 0, this kind of insane, oscillatory behavior, this infinite oscillation happening near 0, is in fact still happening. But it's the y values are being squeezed so that they're so tiny that they're all really, really close to the origin. But even though the y values, even though the magnitude of the y values have been squeezed towards 0, that's what we mean when we say this limit is 0, the infinite oscillations are still happening. And so you can imagine this object, which is following this function, near the origin, is going up, down, up, down, up, down, up, down, up, down, incredibly quickly, but not sort of going anywhere. Well, think about what's happening to the tangent lines. The tangent lines are in fact oscillating back and forth and back and forth and back and forth, those the sort of oscillation of the direction that the function is pointing in is what's causing this function to not be differentiable. So here we have a function which is not differentiable because of some sort of infinite oscillatory behavior. All right, there's a part 2 to this. This is taking forever. There's a part 2 to this, which is like the same kind of thing, but now let it be x squared. All right, this is another function that we have seen before. So once again, I follow this function, but it's undefined at 0 for the same, for the same reason as before. Well, first I'll just introduce it. That's the function. And now the directions say, show that this function is differentiable. Okay, first of all, this function is continuous because the limit as x goes to 0 of x squared sine 1 over x is also 0. Why? Also by the squeeze theorem. It's also true that sine 1 over x is between -1 and 1, so going through the argument again, I can multiply through by x squared, and therefore x squared sine 1 over x is between -x squared and x squared, which means that I have a kind of a quadratic envelope now. And it was in fact last week that we saw that this function is odd and has end behavior kind of like 1 or something. So it's going to go down like that or whatever. Okay. Sorry, its end behavior is x. I don't know what I said, but that's what I meant to say. X, and down here also x. Okay, so something like this. It's a pretty bad drawing, but it's kind of good enough. Since the limit is 0 and since the function is defined to be 0, this function g is continuous at x equals 0. But, says the book, it's also differentiable, which is maybe a little bit surprising. Well, okay, we just do it. What is g prime of 0? By definition, it's the limit as x goes to 0 of g of x minus g of 0 over x minus 0. So if you're just confident enough with these definitions, and it's just a matter of executing them, this is now the limit as x goes to 0 of, well, what is g of x? It's x squared sine 1 over x minus g of 0 is 0, so over x. And that is the limit as x goes to 0 of x sine 1 over x. And this limit is 0. So now, what's kind of happening, you might say? So in fact, g prime of 0 not only exists, so maybe I'll write that. So g is differentiable at x equals 0 because the derivative exists, and in fact, what is the derivative? It's just 0. We calculated that using the definition of the derivative, which is a limit. Okay, so if you want to understand that ends the problem. If you want to kind of understand this, then you have to sort of think about the tangent lines. Now somehow it's like, yeah, it's like these parabolic, this parabolic envelope is sort of pushing the function down so much that it becomes like as flat as the tangent lines to the parabola themselves. Something like that. So this function actually not only is continuous, but even is differentiable, and even this function has kind of like a tangent line, a horizontal tangent line at the origin. And it's the same line, which is of course sort of tangent to these two. All right, maybe I'll leave it at that. Good, let's see, what time is it? I guess I will stop here. Okay, welcome back. It's the next day. We were going over this homework from 3.1 and 3.2, but first kind of an interlude here. We ended with this example of this function, which was x sine 1 over x when x is not 0, and just 0 when x is 0. And okay, we graph this. Let me just do it again, really fast. Looks like this, and the function oscillates infinitely often, but the x is squeezing it so that the limit at 0 is in fact 0, and by patching it up like that, by defining it to be 0 at 0, we have in fact that this function is continuous but not differentiable. So this is continuous but not differentiable. And okay, great. Well, that's one example of a function which is continuous but not differentiable, and there are others in in periods 3 and 4, but not in period 6. Unfortunately, we had this conversation about the absolute value function, which also is continuous but not differentiable. It's continuous at x equals 0. That's because the absolute value function is really just, by definition, a piecewise function, x when x is greater than or equal to 0, and negative x when x is less than 0. So you can think of the absolute value function as just a special case of a more general phenomenon of the a piecewise function, and it's continuous because its value at 0 is 0, and the limit from the left equals the limit from the right. They're both 0. Yet, when I go to compute g prime of 0, sorry for people who already saw this in class, the limit as x approaches 0 of g of x minus g of 0 over x minus 0, that's just the definition of the derivative. Well, what do we get? We get the limit as x goes to 0 of just absolute value x, g of 0 is 0, and over x. And this limit, we know, because we've seen it a million times, does not exist. Why does this limit not exist? Because the limit as x approaches 0 from the left of absolute value x over x is just negative x over x, so that's negative 1. But the limit as x approaches 0 from the right of absolute value x over x is, boom, is now, because x is positive, the absolute value of x is just x, and so that's 1. So this this limit does not exist because the limit from the left is not equal to the limit from the right, and so this function is not differentiable. Okay, so here's like example number 1 of a function which is continuous but not differentiable. Maybe I should keep a color scheme going here of graphing it in blue. So this function is continuous but not differentiable due to like some kind of infinite oscillatory behavior, such that the direction of the function is going up and down infinitely often. That's pretty obscure. This function is not differentiable for maybe a more like boring reason or something, which is that it's sharp here. And there's one more case, which I didn't get to in any of the classes. Let's do it really fast. It's the function, I don't know, okay, I'll just call it h. The h function is cube root x. So cube root x, you might think, is perfectly normal function, and okay, it is, but at 0 something a little bit weird is happening. So that's like 1, negative 1, and the cube root function's got this kind of behavior like that. And yeah, so what's up with that? What can we say about this function at 0? Answer, h prime of 0, well, we can just compute it. The derivative at 0 is the limit as x goes to 0 of h of x minus h of 0 over x minus 0. And once again, we get the limit as h goes to 0 of, what is h? Well, it's just cube root x. H of 0 is just 0, of course. And okay, so we just get this. Well, that is the limit as x approaches 0 of, just simplify via, exponent rules or whatever, that's x to the 1/3 divided by x. So that's 1 over x to the 2/3. And if you give me a tiny, tiny number, positive or negative, and you first square it and then take the cube root of it, you're going to get another tiny positive number. So this is 1 over 0 plus, and this is infinity. So okay, a limit is a number, and here's where it's important that we have that kind of precise understanding. A limit is a number, Therefore this limit does not exist. Even though we write infinity, we really mean that this limit does not exist. And because there's no number that this thing is getting closer and closer to. In fact, it's kind of going off to infinity. And the derivative of this function is by definition this limit. And this limit is infinity, so this limit does not exist. And so h prime of 0 does not exist. This is the kind of new one that I just did. So what's going on here? Here, intuitively, the derivative didn't exist because the direction that the function was pointing kept changing back and forth between 1 and -1 an infinite number of times, infinitely quickly. Here, it's because the derivative changes instantaneously from being -1 to +1. So at the point 0, there is no derivative. Here, I once again forgot my color scheme, which was to draw this in blue. I guess it doesn't really matter, but now, what's going on at 0, you might ask? What's the problem at 0? Well, the derivative is like infinity or something. Okay, you can make sense of that because, of course, this function does have a tangent line, I guess. I suppose it has a tangent line, and that tangent line is the line x equals 0. So that might be, hold on, be back in 1 second. Okay, I'm back, but with a sick 1-year-old sitting here on the floor making noise. We'll see if we can do this for maybe 5 more minutes just to finish up this topic. What is going on this board? 3 examples of 3 functions which are continuous but not differentiable. Continuous but infinite oscillations, continuous but sharp, continuous with a tangent line, not sharp, but the tangent line has infinite slope. And so the derivative is kind of like infinite or something. So, alright, you might be thinking now, having seen these 3 examples of functions which are continuous but not differentiable, is the opposite combination possible? Could you have a function which is... This is not working. Okay, never mind. Could you have a function which was differentiable but not continuous? So the example that you might be thinking is something like, should we do a swap? Okay, the example that you might be thinking is something like, here's a purple Theo, something like a function, I don't know, a piecewise function, which is not continuous. Maybe the simplest thing to do would be something like the x squared function for x less than or equal to 1, and the x squared plus 1 function for x greater than 1. And okay, following up on what we did in class. No, Mama's not here. Mama's at work. She's coming home soon. Close this. Following up on what we did. Oh boy. Following up on what we did in class today, you can see that both of these do have the same derivative. And so it's true that these slopes are the same. What does this function look like? Well, it's definitely not continuous. Up until 1, we have just a regular parabola, but then it sort of like continues up here or something with like the continuation. And so you might, if you didn't think about this too carefully, you might think, okay, what is this slope here at x equals 1? Well, the slope of this line is 2. And then the slope of this line just kind of continues also sort of immediately after with the tangent line of slope 2 as well. This is at x equals 1, I'm referring to the slope being 1. Okay, so the answer is no. Okay, this function f is not continuous at x equals 1, but f is not differentiable at x equals 1 either. And it's maybe a good idea to see this kind of picture sort of once and for all. Theo says, wow! What would it mean to try to compute f of 1? What is... Hey! Hi, Theo! It's the limit as x approaches 1 of f of x minus f of 1 over x minus 1. And, well, taking this particular function that I've constructed, I think this is a good kind of explanation. You'll see that for this function with a jump discontinuity, I just chose arbitrarily to let the to follow the x squared rule, you know, at 1. Yeah, and to follow the I basically I put the hole here and not here or something like that. So in fact, f of 1 is 1. According to this definition. So, when it comes to computing this limit, I think that actually, the limit, I don't even know if you can see that on screen, I'm getting a big hug from my 1-year-old who is homesick from school. The limit as x approaches 1 from the left will be actually, the limit, will actually be f of x, which is just x squared, minus f of 1, which is 1, over x minus 1. And again here, if you do this limit, I promise you, you're going to get 2. So everything's fine from the left, but it's from the right. Now, when I try to take the limit as x approaches 1 from the right, I'm going to get this x squared plus 1 function, but then minus f of 1, which is 1 over x minus 1. And now, in fact, okay, this is actually a little bit kind of weird or something. What are you going to get? You're going to get the limit as x approaches 1 from the right of x squared over x minus 1. And what is that? Well, if x is a tiny bit more than 1, then that's going to be a tiny positive number down there in the denominator, but of 1, wow is right, Thea, 1 in the numerator. And so in fact you're going to get infinity here. And okay, so if you just follow the definition, you get the limit from the left is 2, but the limit from the right is infinity. So this limit does not exist, and so this function is not differentiable. If I want to make, how can I make some sense of the fact that this derivative is infinite from the right? The problem is, yeah, Mama's coming home soon. If I pick a point x, which is a little bit more than 1, after all, I'm taking the limit as x approaches 1 from the right, so it really should be a little bit more. And this is x comma f of x. Well now, if you think about what's happening, the problem is that f of 1 is actually 1. And so this, this numerator, f of x minus f of 1, and this denominator, x minus 1, this denominator is going to 0 here, but this numerator is not going to 0. Why is this numerator not going to 0? The numerator is not going to 0 because when x gets very, very close to 1, then the values I'm considering are right over here. They're sort of infinitely close to this point 1 comma 2. But the actual y value, f of 1, stays down here at 1 comma 1. In other words, in this case, the secant line, whose slope is being calculated inside this limit, is a secant line which, as the 2 points move infinitely close together on the x-axis, the actual points do not move infinitely close together, vertically speaking. That is to say, this line really does have slope infinity, because as x moves infinitely close to 1, the gap between x and 1 goes to 0, but the gap between the y value, f of x, and f of 1 stays big. Specifically, it's about 1, which is in fact what this numerator is right here, right? This numerator is 1. How should I interpret that numerator being 1? That numerator is the difference between f of x and f of 1. F of 1 stays locked down here at the point 1 comma 1, but f of x is way up here near 2. And so we have a sort of an invalid tangent line because the delta x is becoming infinitely small, but the delta y is up at 1. All right, the point of this whole example, and I did want to finish this video while I had all this on the board, is that this situation that I tried to come up with here is not possible. It's not possible for my function to be discontinuous but differentiable. And in fact, there is a theorem, which I'm going to prove next time I am not also parenting, that if your function is not continuous, then it is not differentiable. So not continuous implies not differentiable. And the contrapositive of that, which is the same thing, is that differentiable implies continuous. If a function is differentiable, then it must be continuous. But actually, I think the more common sense way of thinking about it is the one with these negations. If your function is not continuous, then it's also not differentiable. And so I'm going to prove that theorem, although the proof is a little bit maybe boring or something. This is the main idea of the proof is right here. But this is an important sort of thing, and actually this is in our textbook in section 3.1. You can read our textbook's proof of this fact. And okay, what it's going to show is what we've now sort of concluded is all the different ways that a function cannot be differentiable. When you are told that a function is not differentiable, what should you be thinking? Well, first of all, every possible kind of discontinuous function is also a function which is not differentiable. Any function which is discontinuous at a point is also not differentiable there. So infinite behavior, jump discontinuities, holes of any kind. So in fact, any kind of discontinuity, even missing a single point, then the function's not differentiable there. And then in addition to all the ways that we've already seen from 2 weeks ago that a function cannot be continuous, we add in these 3 extra kind of cases of functions which are continuous but not differentiable. Because of sharpness, because of a tangent line with infinite slope, and this one's a little bit more obscure because of infinite oscillation. Okay, I will be back. It's probably going to be like later tonight or something with a proof of this theorem and then finishing going over the rest of the homework from section 3.2. Goodbye. Okay, welcome back. Here we go as promised. A little theorem. Differentiability implies continuity. So this is the way it's usually stated by people. And okay, this is a kind of a conditional. So if a function is differentiable, then it is continuous. But of course, we're not talking about the differentiable in general, but differentiable at a particular point. Calculus is all about local behavior. So what I really mean is that if a function is differentiable at a particular point A, so in other words, if f prime of A exists, then f is continuous at that point. And okay, this is the theorem, how it's usually stated in various textbooks, and this form, if differentiable then continuous, is what we're going to prove, because the proof works better that way. But if you want to actually understand it a little bit better, I think the more natural way of thinking about it is with the kind of double negation here. This is a logically equivalent way of stating it, and it says if the function is not continuous at a certain point, then it's not differentiable. So that's just, I think they still teach these kinds of things nowadays. That's called the contrapositive. So the contrapositive of the conditional if D then C is the conditional not C arrow. If not C then not D. Okay, so these are logically equivalent to each other, but this is the one that we talked about in the previous part of the video, that if a function's not even continuous at a place, then it's definitely not, it's not differentiable. Okay, yeah, well, let's go. How are we going to do this? Well, this is a good example of a theorem which is very easy to prove because there's really nothing to do except use the definitions, but it's hard for people who are not mathematicians because it's kind of not obvious, what to do. So all right, let's do this proof. Let's talk it out. Let's become better mathematicians in the process. What are we trying to prove? If f is differentiable, so okay, maybe I'll even just write that. So assume, for purposes of this proof, assume that f is differentiable at x equals a. Okay, and then, way down here, I'm going to conclude that f is continuous at x equals a. Okay, great. How am I going to do this? Well, what does it mean to be differentiable at x equals a? So then, really, what we know is that just the derivative exists. That's even just how I set it up here. Okay, how am I going to get, simply from the fact that the derivative exists, am I going to prove that f is continuous at x equals a? Well, what is the derivative? It's a limit. And so what I know is that the limit as x approaches a of f of x minus f of a over x minus a, this limit exists. That's kind of what I know. So maybe I put that in a box or something and say like, this is what I know. And what is it that I'm trying to prove? Well, what I'm trying to prove is that f is continuous at x equals a. Well, now I reach for the definition of continuity. What does it mean for f to be continuous at x equals a? Well, that is that the limit as x approaches a of f of x minus f, that the limit as x approaches a of f of x is f of a, is what I meant to say. This is just literally the definition of continuity, and so this is what I need to show. Okay, so actually, when you sort of break it down now, the definition of continuity is phrased in terms of limits. The definition of the derivative is phrased in terms of limits. So I really just have like kind of a limits problem now. And all right, f of a is just a number, and so yeah. Well, good. What do we do now? Hold on, I'm trying to remember how this theorem works for a second. Right. So really, oh yeah. Oh my gosh. Okay. So really, okay, here we go. So really, I need to show that okay. So here's my plan. My plan is to prove that the limit as x approaches a of f of x minus f of a, that this is 0. If I can prove that the limit as x approaches a of f of x minus f of a is 0, then limit laws will enable me to conclude that the limit of a sum is the sum of the limits, and so if that's true, then it must be true that like the limit as x approaches a of f of x, in other words, split the limit up, but that's just a constant, right? Plus f of a is 0, and just then by minus f of a is 0, and then by just moving that f of a over to the other side, then that gives me the definition of continuity. Okay, so everything just hinges on showing this little fact. And so, okay, let me just begin. The limit as x approaches a of f of x minus f of a, somehow I need to show that this limit is 0. Why should this limit be 0? Well, it's not obvious kind of how to do this, and maybe now is the time for sort of like a picture or something. So here's kind of like a picture, yikes, of a function, and here is x, and here is a. No, sorry, other way around. Here's a and here's x. So what do I know again? I know that the derivative exists. And so this is a comma f of a, and this is x comma f of x. Okay, and what do we know? We know the derivative exists. What's the derivative? It's the slope of the tangent line to the curve. But I draw in my secant line, and I draw this whole thing again. So that's f of x minus f of a over there, and that's x minus a. Okay, and so here's essentially what's going on. We could be done with this in just like 1 minute. This limit exists because I'm assuming that f is differentiable. So therefore, f prime of a exists, and this is f prime of a. What does this mean? This is, as x gets, what this is really saying is that as x gets really, really close to a, yes, this bottom goes to 0, of course, but the numerator also goes to 0, and therefore I have a 0 over 0 situation, and yet this turns out to be some kind of number. Another way of looking at this is that as x gets infinitely close to a, this thing in the box is saying, as x gets infinitely close to a, yes, the gap between x and a gets really, really tiny, but so does the gap between f of x and f of a. And so, if all I need to do is show that the gap between f of x and f of a is 0, well, of course it has to be 0, right? Why does it have to be 0? Because if it weren't 0, that's maybe one way to think about it. If this numerator weren't 0, then the denominator would be going to 0, and the numerator would be going to something else. And something else that's not 0 over 0 is sort of undefined. But I know that this derivative exists. Alright, so how do I actually do the proof? Well, if the only thing I know is that this limit exists, that suggests that I should multiply the top and bottom by x minus a. Okay, this might feel like kind of like a cheat or something, I don't know. Or this might feel just like a brilliant, wonderful idea. But inside this limit, just multiply by x minus a over x minus a. Why? Well, first of all, you're allowed to, because that's just 1, and x is approaching a, x is never equal to a. Okay, and now what does this limit turn into? This limit turns into, by limit laws, the limit as x approaches a of f of x minus f of a over x minus a times the limit as x approaches a of x minus a. In other words, just split this up now into two things. What's this? This is f prime of a. Here I use the assumption that this limit exists simply to justify this limit law that says that the limit of the product is the product of the limits, provided that they both exist. So the legitimacy of splitting this up has been justified now because that limit does exist. What's this limit? Oh, it's just 0. And so I've shown that indeed that this limit is 0. So okay, but the sort of takeaway, so the proof is done. The only really sort of understanding that's needed is this one. You should be looking at this and you should be saying, okay, look, if this derivative exists, then I know that this limit is 0, because that's just saying that the numerator goes to 0. Well, the numerator has to go to 0 if the derivative exists, because if the derivative exists, then the only way for if this denominator, since the denominator goes to 0, the only way for the ratio to exist is if the numerator goes to 0 also, giving rise to a 0 over 0 situation, and then turning out to exist. So that's all we've done here, is we just kind of use the technical language of limits to prove this, that this numerator does go to 0, and therefore that the limit as x approaches a of f of x is actually f of a. And therefore, by the definition of continuity, this function is continuous, and so we've shown this version of the theorem has just been proved. If the derivative exists, then the function is continuous there. And the reason why this is important, I already said in the earlier part of the video, that now we have sort of a complete characterization of all the ways in which the derivative cannot exist. Whenever the function is discontinuous, the derivative doesn't exist, and then also sharp points, infinite oscillations, and vertical tangents. Okay, back in a minute for going over the 3.2 homework. Okay, finally, getting back to just going over the rest of this homework. This was section 3.2. This was the first homework that you had to do after learning the power rule. And okay, let's go. They ask for, I think they just say like, find the derivative or whatever. Okay, so this is just the curve y equals 8. What is the derivative? The answer is just 0. Oh, there's a little bit of new notation that just kind of like creeps in. I'm going to talk about this more later, so for now let's just not worry about it too much. But there is this notation dy over dx, which is pronounced dy dx. And for now, it just means the derivative again. So anyway, the derivative of a constant function is just 0. Okay, that was pretty easy. Number 6. Y equals 1 over x to the 8th. Well, as I talked about in the video where I taught the power rule, and also as I talked about in class in the follow-up day, the best thing to do is to write this in a derivative-friendly form as x to the negative 8th, and now it makes it more clear how to apply the power rule. And I convinced you in class today that the power rule was applicable to functions whose exponent is a negative integer. Well, what does the power rule say? The power rule says the derivative of x to the something is negative 8 x to the, and then you go down a power, so to the negative 9. And so I personally would write my final answer as negative 8 over x to the 9th, because I like to get rid of negative exponents in my final answer. Okay, that was number 6. Number 11 is just a polynomial. So the f function is negative t squared plus 3t minus 6. Well, the great thing about knowing all these rules is that because the derivative of the sum is the sum of the derivatives, it means that if I need to differentiate a function, I can just differentiate all of them individually and then add them all back up. And okay, anyway, just doing this just takes like seconds, right? What is the derivative of t squared? It's 2t. And so this is negative 4t, and the derivative of 3t is just 3, because, you know, that's just a line. The derivative of negative 6 is 0. So, done. 16, another just polynomial function. How do we find the derivative of it? Man, you just do it. What's the derivative of x cubed? Well, it's 3x squared. So that's 6x squared minus 8x plus 3, done. Okay, 25, the book makes a big deal about rewriting this. Okay, me too, you know, careful people will not get confused and will recognize that 5 over 2x squared really means 5 halves x to the negative 2. So I think it's extremely important to take this extra step to rewrite your function with negative exponents in such a way that you can easily apply the power rule. I call this differentiation-friendly form. And now I'm ready to actually differentiate, and yeah, what I get is 5 halves times, bring down the negative 2, x to the negative 3. And so my final answer is negative 5 over x cubed. Okay, great. That was 25. 33, kind of a silly problem actually. It says, hey, consider this function, negative a half plus 7/5 x cubed. What's the derivative? Well, the derivative of negative 1/2 is 0. The derivative of 7/5 x cubed is 21/5 x squared. And now they specifically want to know what is the slope of the tangent line at 0, comma, negative a half. I'm not sure why they wanted you. It feels a little bit dumb to ask for the derivative at 0, but there it is. I'm going to plug 0 into this function, and the answer is just 0. Okay, 45, I think the directions were just find the derivative, right? So here, once again, if you know what you're doing, you know, this takes 1 second. What are you supposed to do in this problem? You're supposed to realize that the square root of x is really just like x to the 1/2. And you're supposed to realize that the cube root of x is really just x to the 1/3. And now these are just power functions, and so the power rule is applicable. And now we take the derivative, and what do we get? Well, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. That's what the power rule says. You go down a power. Minus 6 times, what's the derivative of x to the 1/3? Answer, 1/3 x to the, I subtract 1 from 1/3, and I get negative 2/3. So there's a certain amount of algebra going on here. You could just leave it like that, but almost everybody, including me, will take the extra step to rewrite it without negative exponents. So what is x to the negative 1/2? Well, it's 1 over x to the 1/2. In other words, this is 1 over 2 root x. And that becomes minus 2 over x to the negative 2/3 is like 1 over x to the 2/3. So that's how I would leave my final answer. So that's 33, that's 45, 63 with that hard problem that we did in class. So let's just do these last 4 now, and then we'll be done. All right. Instead of stopping the video, I'll just take 1 minute and erase this. Hope I am recording, yeah. Good. These last couple were hard, but I don't think they were as hard as the one we went over in class. Anyway, here it is, 76. What does 76 say? Show that the graph of the function, so here is my function, x to the 5th plus 3x cubed plus 5x. Show that this function does not have a tangent line with slope 3. Does not have a tangent line with slope 3. Okay, well, fortunately this is just a polynomial, and so I can differentiate this function in like a second. What is the derivative of this function? 5x to the 4th plus 9x squared plus 5. And according to what I'm supposed to show, this derivative, the derivative is the function which outputs derivatives, and the derivative is the slope of the tangent line. So I'm supposed to prove that this function does not have a tangent line with slope 3. In other words, the derivative of this function is never 3. Well, what's wrong with the derivative of this function equaling 3? Well, set the derivative equal to 3, and, well, there it is, right? 5x to the 4th plus 9x squared equals negative 2, and that's just not going to happen, right? The left-hand side of this equation is always positive, and so there's just no way for these two to add up to be negative 2. Therefore, since this equation has no solutions, this equation has no solutions, and so the derivative of this function is never 3, and so this function never has a tangent line with slope 3. Okay, I thought that was relatively straightforward. 77 is, I think, actually kind of tricky. Not quite as hard as the one we did in class, but still sort of hard. The directions are a little bit weird, but all right, they give you a function, f of x equals equals root x, and they also give you a point, and this point is negative 4, 0. And what they say is, find an equation of the tangent line to the graph of the function through this point not on the graph, and find to find the point of tangency on the graph of f, solve the equation. All right, so this is, I find these directions to be actually like a little bit annoying. So let's just read the first sentence. And what does it say again? Find an equation of the tangent line to the graph of the function through the given point. Alright, this is calling out for a picture pretty heavily. So, so let me make a picture now. And so my picture looks like this. Here is my square root function, 1, 1 or whatever, and then like 4, 2, and etc. And that's roughly not so bad. Okay, great. That's my function f, the square root function. Then there's this point, negative 4, 0. Notice that this point, negative 4, 0, is just like very obviously, not on the graph of the function. What am I supposed to be doing? Find an equation of the tangent line to the graph of the function through this point, which is not on the graph. Okay, in other words, they want me to find, looking for a something to use as a kind of a model, but I guess I don't have anything. But you find the equation of the line which is tangent to the graph of this function, but also goes through this point, negative 4, 0. In other words, take, do I really not have, I need like a stick. and I just don't have a stick. Well, that's it's very annoying that I don't have like a meter stick. I guess I kind of have. Here's my closest thing. This is in fact my 2-foot radius compass, which I use for geometric accurate chalk drawings on my sidewalk. Well, this is the closest thing I have to like a meter stick. What am I supposed to be doing again? It's supposed to be tangent to the graph of this function, but going through the point -4, 0. So it's like you just kind of stand here at the point -4, 0, and just sort of like take a line, just like drop it until it bumps into this function. Right? This function is just like a kind of a giant boulder. So take like a long stick, stand at -4, 0, and drop your stick. Wherever your stick lands, that's the line which is tangent to this function. Okay, so if I now draw in this tangent line, the thing is I don't know where this tangent line is going to land. My very crappy drawing indicates that maybe somewhere around 5-ish or something is where this line will be. Okay, so this is similar to the problem that we did in class today because I need to find the equation of this line, but I don't know anything about this line right now. Like I don't know the slope of this line, and I also don't know where this line is tangent to this function. So yes, it's possible for me to differentiate this function. The function is root x, so that's x to the 1/2. So what is the derivative of x to the 1/2? It's 1/2 x to the -1/2. We just did this kind of a minute ago. So yes, I have a rule which tells me for any given input what the derivative will be there. But this rule is useless because I don't know what number to plug in to this function because I don't know where this line is tangent. So I need to do that bold thing that I did in class today, and I need to give this point a name. I need to say, okay, let me call this point like, I don't know, A. Let A be the x-coordinate of the point. This point is determined, I just don't know what it is, right? There's only one answer to what A could be. I just don't know it yet. What do I know about A? I know that the y-coordinate is like root A. So I'm going to call that point A comma root A. Okay, well now, having given that point a name, I can give an answer to what is the slope of this blue line. And the answer is, if I just plug in A into the derivative function, I get 1/2 root A. Okay, so on the one hand, the slope of this line must be 1/2 root A. Why? Because the derivative of the function is the slope of the tangent line to the curve. And this blue line is the tangent line to the curve at A. And so its slope must be the derivative at A. Okay, but on the other hand, now that I've given this point a name, I can see that I really have 2 points. And so it's possible to give a different account of the slope of this blue line. The slope of this blue line is also just sort of change in y over change in x for these 2 points. So the slope of this line is just delta y over delta x. In other words, it's the height, which is root A, over the delta x, which is a minus -4. Okay, so if you see kind of what's going on here, I don't know what this point is, I give it a temporary name, I then realize that I can express the slope of this line in 2 different ways. One, using the definition of the derivative as the slope of the tangent line to the curve, but also with these 2 points I see that, you know, the slope is just, can be calculated just using kind of algebra 1 means. And therefore, what is this point A? Well, it's whatever point satisfies the equation root A over A plus 4 equals 1/2 root A. So I set these two different calculations of the slope equal to each other. This to me is the clearest way to do this problem. Okay, I cross multiply, it gets 2a equals a plus 4, and so a is 4. Okay, and that's not kind of a crazy surprise actually. The answer now to this problem is that this is apparently all happening at 4, 2. Well, I can check this now because what is the slope of this line? Well, on the one hand, I go up 2 and over 8. And so the slope of this blue line is 1/4. But on the other hand, I can just plug in 4 into my formula for the derivative, and the answer is it's 1 over 2 times root 4. So that's 1 over 2 times root 4. Well, that's also 1/4. So indeed, that is the right answer. That is the point of tangency of this line. Okay, good. 2 more, and I think they're not so hard. 89, 113. Let's go. Okay, 89 says it gives you a certain function, and the function is f of x equals -1 over x, and on the interval I believe 1, 2, yeah. And here the book is just trying to strengthen your confidence with with average rates of change, instantaneous rates of change, and stuff like that. Problem says, find the average rate of change of function over the given interval. Compare this average rate of change with the instantaneous rate of change at the endpoints of the interval. All right, so this is not so hard. It's more of a kind of a vocab thing. What does the -1 over x function look like? Well, it looks kind of like this. So here's like when I plug in 1, I get -1, and by the time I get to 2, it's -1/2. So that's -1/2, 2, boom. Okay, and then the function, I guess I could plug in even like a half and I get back 2. So my function's kind of looking like that, my curve. Something like this. Okay, great. Question number 1. What is the average rate of change of f on the interval 1, 2? The average rate of change of a function is just the total change over the width of the interval. So what we're looking for here is the change in f over the change in x. How much does this function change? Well, here is the point 1, -1. Here's the point 2, -1/2. And so what I'm looking for is just, well, this is just f of 2 minus f of 1 over 2 minus 1. So it's just like the derivative, but now, without the limit, right? This is just the slope of the secant line. In fact, that's exactly what it is. The average rate of change of a function on an interval is just the slope of the secant line on that interval. It's just like average velocity, but now, it's not necessarily a position versus time curve, so we're not necessarily finding the average velocity. It's just a function, and we're finding the average rate of change of that function. So, okay. We're really just calculating, therefore, the slope of the blue line, right? Change in y over change in x. And, of course, what is f of 2? We already said it's -1/2, and f of 1 is -1 over 2 minus 1, and so I guess we just get 1/2, right? The slope of that blue line is just a half. You go up a half and over 1. Okay, so on average, you could now say, on average, this function has changed by a half. Okay, because it took me 1 unit to achieve a change of 1/2. And now it says, compare this to the instantaneous rate of change of this function at the endpoints of the interval. I think those were the directions, right? Yeah. Okay, so for that I need to do calculus. None of this is actually calculus yet. So what is this function? It's -1 over x. In other words, it's -x to the -1. And so I can, when I differentiate, I'm going to use the power rule. power rule says bring that number down, so this is just x to the negative 2. In other words, the derivative function is just 1 over x squared. Okay, so what is f prime of 1? Well, it's just 1. And what is f prime of 2? It's just 1/4. Okay, so if this is a position versus time curve, then the slope of the tangent line at x equals 1 is the instantaneous velocity. And we have just seen that this is in fact 1. The slope here is 1. But, okay, and what about and then what about at x equals 2? At x equals 2, the slope of this purple line is 1/4. So, alright, so what we see is there's this function whose instantaneous velocity at time 1 is 1. By the end of the interval, the instantaneous velocity is 1/4. On average, the average velocity on this interval is 1/2, because that's 1 and that's 1/2. So okay, so it's changing sort of quickly at first, and then by the end of the interval it's changing slowly, but on average it's 1/2. Okay, that's really all there is to say about that, I guess. Alright, last one. 113, and then this freaking long video will be over. What is 113? Okay, this is kind of like a little tricky. We have this function which is ax cubed when x is less than or equal to 2, and x squared plus b when x is greater than 2. And the directions are find a and b such that such that this function is differentiable everywhere. So I'll just say make f differentiable everywhere. Okay, well, of course, to the left of 2, this is just a cubic polynomial, so it's differentiable everywhere. To the right of 2, this is just a quadratic polynomial, which is differentiable everywhere. So there's only one point where things could potentially go awry, and that's at x equals 2. And so, okay, now you need to sort of be thinking, based on that little theorem that we proved in the middle of this video, that differentiability implies continuity. Or, better put, if a function is not continuous, then it's not differentiable. So in order to ensure that this function be differentiable, we first must make sure that this function is continuous. So I'll just write like something like f must be continuous at x equals 2. In other words, well, just the two pieces have to meet, right? So what can I say about f of 2? Well, actually, f of 2 is just, if you plug in 2 here, you just get 8a. And so, actually, well, while that's true, it might be simpler to just say, okay, what has to be true? The limit as x approaches 2 of this function has to equal f of 2. And also, the limit has to exist. In other words, the limit as x approaches 2 from the left of this function has to equal the limit as x approaches 2 from the right of this function. And so, in other words, the pieces have to meet. Well, what is the limit as x approaches 2 from the left? If you plug 2 into that cubic, you get 8a. And if you plug 2 into the quadratic, you get 4 plus b. And therefore, 8a, the limit from the left, as x approaches 2 from the left, has to equal the limit as x approaches 2 from the right, which is 4 plus b, in order for this limit to exist. And then, of course, f of 2 is just 8a. So that will make the function continuous. And then also, the function must be differentiable. So what is the derivative of this function? Well, doing it the short way and just differentiating the pieces one at a time, we get that the derivative of this function is 3ax squared when x is less than or equal to 2, and the derivative of this function is 2x when x is greater than 2. And this function tells you the slope of the tangent line all the way up until 2, and this one tells you the slope of the tangent line sort of afterwards. So I need these two to be the same, right? And so at 2, well basically I guess I need to say this, that the limit as x approaches 2 from the left has to equal, the derivative of 2 from the left has to equal the derivative of 2 from the right. And the derivative of 2 from the left is, well, plug in 2 here, and you get 4 times 3, you get 12a. And the derivative of 2 from the right is just 4. So, this also must be true in order for the slopes to be the same. So it's really like a two-part problem. The pieces need to meet so that the function is continuous. That's like you don't drop the baton. And also you need to pass the baton smoothly. And in order to pass the baton smoothly, you have to make sure that the rate at which this function is increasing is exactly equal to the rate at which this function is increasing at the moment at which this function takes over from this one. And so you can just differentiate them 2 pieces at a time, find what these two numbers are, and okay, well, there it is. Now I just need to make sure that both of these are true. Well, what do I get? A is 1/3, and if A is 1/3, then 8/3 has to equal 4 plus B. So what is B? -4/3. Did I do that right? 12/3 minus 4/3 is 8/3. Why am I doubting myself? A is 1/3. 8/3 equals 4 plus B. So B is 8 minus 12/3. Yeah, that just seems right. Okay, so I think that the answer to this problem is 1/3 x cubed and x squared minus 4/3. That this is the answer. This for x less than or equal to 2, and this for x greater than 2. I suppose you could even like check it or something. Plug 2 in here, and you get 8/3. Plug 2 in here, and you get 12/3 minus 4/3 is 8/3. So the function's definitely continuous. The derivative is x squared, so that'll give you 4, and the derivative here is 2x, so that'll also give you 4. So yeah, this is good. Okay, I won't bother drawing it, but if you want to draw it, I don't want to draw it. I'm done. All right, good. Bye.